let's review the basis of skeletal structures. And skeletal structures, and sometimes I'll just commonly refer to them as zigzag structures because it'll look something like this. What you want to do is understand that every termination point represents a carbon. So there's a carbon right here, that's a CH3. There's a carbon right here, that's a CH3. And then every vertex or bend in the chain also represents a carbon. There's one here, here, and here. So this is a 5-carbon chain. Even if you have branch points, something like this, every place where a chain ends represents a carbon. And then every vertex represents a carbon. The hydrogen on every carbon are implied. And what you want to do is assume that there's enough hydrogen on each carbon such that it has 4 total bonds. Let's just look at a couple of carbons in this molecule. The carbon on the far left. In the drawing, 1 bond is shown. We have 1 bond to the neighboring carbon. But we know that the carbon must have 4 bonds total, so this carbon must have 3 implied hydrogen. Likewise, if you look at this carbon right here, in the drawing, 3 bonds are shown. There's 1, 2, and 3, so there must be 1 implied hydrogen to give it its 4th bond. Don't let double bonds throw you off. So for example, if we have this molecule here and you're looking at the carbon that I've highlighted, we want that carbon to have 4 total bonds. Here's 1 bond. This sigma bond makes the 2nd bond. The pi bond is the 3rd bond, so there must be 1 implied hydrogen. If you have a heteroatom, it must be drawn in. And heteroatoms are things other than carbon and hydrogen. So things like oxygen, nitrogen, sulfur, and halogens. Those must be drawn in. Let's look, for example, at a 4-carbon chain. Right now we have 4 carbons. If one of the termination points ends up being a heteroatom like a chlorine, that takes the place of the carbon on the end. So now, instead of 4 carbons, there's only 3 carbons. So don't get confused and think there's a carbon here and the chlorine. The chlorine took its place. You can also have a heteroatom within a chain. Like this. So in this case, we have 4 carbons and then an oxygen in the middle of the chain. If your heteroatom has hydrogen, you must draw them in. So let's say this chain ends with an oxygen. You can't just leave the hydrogen off of there. So we know the oxygen has 2 bonds, and we have an OH group. So you need to draw that in. You can attach it directly to the oxygen or draw a bond. Likewise, let's say you have a nitrogen within a chain. This nitrogen needs 3 bonds total. 2 bonds are shown. The 3rd bond is to a hydrogen. Because it's not a carbon, you can't leave that hydrogen implied. You must draw that in. As for lone pairs, it's up to you whether or not you want to draw them in on the skeletal structure. You don't have to, but you can include nitrogen's lone pair and oxygen's lone pairs. If you have a triple bond, you want to draw those linear. The reason for that, let me just draw a simple molecule. That's because these carbons are sp hybridized. Sp hybridized carbons are linear. And we want to show those accurately. So if I'm going to just draw this top structure, you might be tempted to want to do it like this and show your 4 carbons and put the triple bond there. Now that's sometimes accepted, but it's really not ideal. Instead, the way you want to draw this is completely linear. So I'll draw the triple bond and draw the CH3s coming off of that. And you know that these are carbons because that's a transition point between the single and double bond. And if it's in a slightly larger molecule, let's just say Cl, CH2, CH2, C, triple bond C, CH2, OH. If I'm going to draw this, for me the easiest way is to start with my triple bond. Draw your 3 lines and make the triple bond. Then add the groups on the right and the left. So on the right, we have a CH2OH. So here's my CH2, and then I'll make a bend to go to the OH. On the left side, I have a CH2, CH2, Cl. So draw a line, here's the CH2, make a bend for the next CH2, and then the Cl.